You want to see it?
All right, let's get started, guys. It's 2:00. All right, let's get started. So last week, I believe we covered, we did the iris data set and also the wine data set, both of them for classification, right? And I believe I'm looking at the script here for torch wine. So we went over it. So I'm going to double check that I loaded that notebook. Machine Learning Foundations, 2025. So we did, you can see in-class torch wine. So I added that Jupyter notebook. We've done iris and wine for classification, right? So we're trying to predict labels, etc. And we did that. But I chose the wine data set to be used for both classification and regression, right? So now today we're going to do regression, and you'll see it's very similar with very minor changes, right? And that's kind of the idea. So this week I'll be talking about a little bit of regression, and then also we'll talk about cross entropy, one of the other loss functions for classification. So that's kind of the goal. I'll be posting the homework assignment sometime on Wednesday. And then next week we have spring break, of course, so you guys will be off. Yeah.
When would this homework assignment be due?
This new one, a couple of weeks after spring break. It's not going to be during spring.
Oh, so it's a couple weeks after spring break. It'll be.
Yeah. Yeah. This is, like I said. I mean, you already know how to do deep learning, right? You should say yes, right? You already know how to do deep learning. So we've met like one of the major objectives of the course. We've done 2 deep learning examples actually with 2 data sets, iris and wine. And today, as I said, all I'm doing is a regression model showing you a little bit of the logic there. Yeah, and so that's after these topics, cross entropy and this one, we're essentially at advanced topics, right, for the semester, like image processing, things like that. All right, which will be the next data set. It'll be something like the MNIST data set, which is images essentially, but it's, you'll see is very similar. Just things are going to be larger, of course, etc. I also need to do a demo on something called Colab or Kaggle. I haven't done that in this class, have I? No. Yeah. Oh, did I do that already? Okay, perfect. All right, so you guys already know that. So Colab, look at the videos from last week. It should be in there then. And those are solutions that you can try out for GPUs. Okay. Given right now you haven't needed GPUs, but going into image processing, you'll definitely need because they're much larger. Yes, sir. Yeah, I haven't decided yet. That's kind of the maybe. It might be Sci-Far 10. I just haven't decided. Yeah, I'll definitely provide the data set. I'm thinking it'll be Sci-Far 10, which is a big data set of color images. So itself is not difficult, but really what's going to be fun or the challenge of that homework is the mass, the size of the data set and the headaches that creates for you. You see that? So that's really where the value is, as I think, I'll provide the code and everything. Got it? Yeah. So for those, I mean, I've been thinking about it. I believe it's going to be Sci-Far 10, but I haven't made the final decision. Okay? Everyone with me? All right. But today we're doing in Sci-Far 10 is classification again, but today we're focusing on regression problems. So this is very common. You do, some work for anyone usually. It's going to be like a type of a regression problem. You're trying to predict some kind of a quantity. So yeah, so we've done in-class torch wine, in-class torch iris. These are both classification tasks. I already set up my Jupyter notebook here. I was looking at in-class Torch Wine, and you can see this is what we did last week. And we completed. The results were not great, given that actually this data set is essentially for regression, but I was playing with it for classification, and I gave you some thoughts on what you should do. All right, so I'm going to go ahead and close this one. I'll remind you, let me just turn this off. I'll remind you guys that you should be reading this document. Everything that I'm saying, like the essence of this whole course, is summarized in this blog post. Please make sure that you read it. It'll be on the exam. All right. So let's go ahead and take a look. So it's going to be sort of the table of contents. All right. Here, we've been focusing on this here. And we can go to the repo torch, click on that. All right, we are at the repo, and you can see we've done iris, wine, and today we're just going to look at regression and something called XGBoost. So this is going to be our example for today. My computer is slow. All right. So you can see this is the Jupyter notebook that we'll be using today. It's similar. It's going to be the same wine quality data set. I'll go through the whole thing. But one of the issues here, if you notice, is that the Y will be just one field, right? So we're going to have one output neuron that is going to predict a regression value. In this case, it's going to be that ranking, essentially. All right, so let's get started then. So I'm going to call this one in-class regression torch wine, essentially. So I'm going to click on new. Here we are. So again, guys, it almost seems repetitive, right? And that's the beauty of it. It's like this initially, you saw the perceptron, it was maybe terrifying because so much was different. But as you can see at this point, this is the third time that we've done something where like 70% of it is exactly the same. You see that? And if you continue following this template, it's always like this. And you now have a sense of, okay, I just need to change these areas. These areas stay the same. If I'm consistent in the way that I process my data, I can fit it into my X's and my Y's. And then you can start solving a ton of problems. And then what has to happen, as will happen in the SciFar 10 homework, is now you'll be dealing with images. And so you're able to solve that data set using the techniques you know about, right? So you'll be able to solve it. You can take some image data Just do like a little thing and you can solve it. But to solve something that is image-based, you probably need a new set of techniques to add to your code. And that's going to be an algorithm called convolutional neural network. So that's where we start to go from just plain vanilla feed-forward deep neural networks to the more advanced deep learning algorithms, of which there are several. So the advanced deep learning algorithms are convolutional neural networks, is extremely powerful. GANs, generative adversarial networks, autoencoders, right? And transformers. And transformers are essentially the thing that created ChatGPT, for instance, right? So these are the advanced algorithms of deep learning. And the way that I would like to do this is I'm going to give you the Sci-Far 10 homework, and I'm going to ask you to solve it with the tools that you know about, which means you don't know how to use convolutional neural networks yet, right? And then you'll solve it, get a performance of some, and then we'll start to add, more advanced techniques, CNNs, and then something called transfer learning and a ResNet. And so that will kind of, let you, allow you to understand how deep learning works. Okay. But anyway, so for now, we're just going to do the regression problem. All right. So let's call this in class regression. This is the wine data set. So regression wine. Yeah. Maybe torch. Okay, so that's the name. All right, so this is going to be similar. I'm just going to go to the notebook, on the repo. I'm going to add the libraries. So NumPy, Torch, Pandas, sklearn, Torch NN, Torch functional, Optim. Okay, same libraries as before. Hit run. Give it a second there. Processing. All right, finished. Then we're going to go a few more libraries. Okay, I'm going to add them here. Hit run. Matplotlib, sklearn for train test split, Torch utils for the tensor dataset, tensor data loader, which is really helpful, sklearn. I also want to use this opportunity to use XGBoost. XGBoost is not a regression. Sorry, yeah, it's not a neural network based algorithm. Okay, this is more similar to what you use in Weka when you were using decision trees and random forests. So XGBoost is a type of a tree-based machine learning algorithm, okay? But it's like the state of the art. It's like the best one that you have available, and it has its own library. So in this context, we'll compare the results of neural networks versus XGBoost and they're very good for like regression data sets, basically. So not every, just because you're using a neural network doesn't mean that you're going to get the best results, right? So sometimes there are other tools that are useful. And definitely XGBoost, I've noticed, does really well in competitions, right? So it's not installed. So we're going to have to install it. Okay. So I'm going to do pip install XGBoost. All right, so let's go ahead and run this one. Give it a second there. But yeah, I've worked on problems and I spent a month trying to every possible neural network architecture. And then I just did XGBoost and it was better. And people just want best results. They don't care honestly what you use. Um, so this one's really, really good. Okay, so it installed successfully. And XGBoost. So import XGBoost is XGB. So this is a library. It's very much of a black box type of thing. So really, we just have to learn how to give it the data, but we'll be processing the data for the neural network also. All right, so now I'm not going to show Onyx today, so we don't need anything related to Onyx. Now, as you can see, we just start moving in to the parameters. So the parameters are the batch size. So for the neural network, so everything that I'll do is mainly for the neural network. And then at the end, I will switch gears to XGBoost. And then we can compare the two models. So I have the batch size here, 16 samples. The learning rate is going to be, notice, 0.005. You can change that to 0.001. This is a parameter that is kind of experimental. You got to play with it. N epochs, about 100 epochs. Epsilon, you guys know it's for divide by zero errors. So same parameters as before, okay? So a lot of it is very repetitive in the machine learning pipeline. Okay. All right, then we are going to read in the data. So remember, this is the wine quality data. All right. So wine quality, this is in the current working directory. So I'm going to remove this data part. Okay. I'm using pandas to read in the data, read CSV. The delimiter, I believe, is semicolon for this one, which is similar to what we have done. Right? Data has been read in. Then I'm going to just look at the pandas data frame. This is important as we have to decide, right? So we have to make some decisions here. So essentially, we're going to have, this is not a classification problem anymore. This is going to be a regression problem. So when you have regression problems, you can have multi-output regressions. That's possible when you're trying to predict, let's say you were looking at some data and you're trying to predict the price for 3 stocks or 5 stocks, right? For every day, you want to say, the stock for, I don't know, NVIDIA, right? And it's going to be 3,000, 3,500, and the stock for Microsoft is going to be 65 or whatever it is. So you can predict multiple values at the same time, or you can just predict one. So in this case, we're just going to have one neuron to predict this value, the quality. So that's a value essentially between 0 and 10, right? But it could predict like a 3.7, 6.9, because it's going to be a real valued number now. And then the inputs are going to be the same labels, which is, I believe, it's 11. So this, it's 12 columns, so 11 features. So a vector of 11, that's the input, and a vector of 1, that's the output for one specific neuron. All right, that's it. If you had multiple outputs, you might want to scale those values, but since we only have one, that may not be necessary for the output values. We still want to always scale the input values. All right, so I'm going to go ahead. So I printed the pandas. Now let's go, same thing. I like to look at the columns. I like to do the correlation matrix just to give me a sense of what's going on. So I've got my fields there. Pretty consistent. All right. So we've got that. Now, as I've shown you, you can select just a fewer columns. You just want to focus on a few. Now let's plot the correlation matrix. Same as before. Give it a second there. All right. So remember the thing in question is quality. We had determined that alcohol is positively correlated. It has a strong influence with 0.44. And then negatively correlated, I believe we had said density, and that was minus 0.31. So those are the results that we had before. Starts to give you some insight. There's the model. Okay, so I'm going to save this. Going now, we start to process the data just like before. We convert our pandas frame into a NumPy array, as you know, pretty standard. We can look at the NumPy now. It's not a pandas anymore. We got our NumPy array there. Make sense? It's too easy, right? So there we are. So, follow the procedure. So I'm gonna look at, so now we start the slicing of the data. I got my shapes, obviously. You live by the shapes in neural networks, as I said. So that's pretty important. So we have 4,898 samples, the 12 columns. We're going to slice out X and Y. So same approach as before. We got my X data, the first 11 columns, and then the ratings are the last column. So I've got that established. We're going to take a look at the Y's. So here, the Y's, we look at them. They're float values, right? So the individual ratings. And then here, this is where the differences start to show. In the classification task, we wanted to convert these values in Y to integers, right? So because they were classes to discrete values, here we don't have to. These are going to be regression values, okay, that we are going to train our model. Then we can proceed to print out the shapes because we have sliced, and you can see 4,898, 11 input vectors, 1 output vector. Okay, there we are. Easier to do the regression for this data set than the classification. I'm going to do the random seed. Right, so I can randomize the data every time. And then I'm going to do my familiar train test split. So a lot of these things, as I said, you'll be doing this for a very long time, right? So you run train test split and boom, there we have it. So we got our X and Y now converted into X train X test, Y train Y test. We are ready to train the model and then to evaluate. And then our goal today also is to compare with this other method called XGBoost. All right. So we can print out the shapes here. So it's going to be 3,000, almost 4,000 training samples and 980 test samples. Okay. We're going to do the float type, remember. I'm going to convert these to 32 bits. If you notice, all of them actually. Here they're all float, and I'm going to convert them to NP float 32. Right? X and Y. This is a little bit different from the previous example. Everything is just, float, essentially. And now we convert them into torch tensors from NumPy. And there we have it. So we have our X train, X test, Y train, Y test, all as torch tensor. Very consistent. Now comes, again, the normalization. You always want to normalize your data, as I explained to you. So we just calculate the X means and X deviations. So we've got our X train TR and our X train TR, the mean and the standard deviation, and save those into our vectors, essentially. We can once again visualize these so that we don't lose sight. Basically, we average across columns, right? And we calculate standard deviations across columns, such as this one over here. And there you have it. Is this concept clear of calculating the means and the standard deviations? All right, perfect. All right, so we have that. So I'll skip the deviations, but we've already collected it. So now create the data loader. So, when you do images, when you do transformers, you should use a data loader, right? So just mastering that skill is really important, understanding how to do that. So I'll type here markdown. Oops, not that. Maybe that one is code. Sorry about that. All right, so let's add a few more cells here. And now we're going to create our data loader. So here, so notice here, the data can also go directly into this tensor data set like this. So this is another example of the multiple formats that are allowed in tensor data sets and tensor data loaders, okay? So before we were creating a list of tuples, if you remember, of the vector and the label. Here in this regression task, we can just take X train and Y train TR as they are as torch tensors. Notice that they haven't been modified, right? So they were just in this format, kind of like that. Does this make sense, guys? And then we just load it into tensor data set. There we are. So that format is also allowed. And then we create our data loader. Data loader is just train DS, the batch size of 16, and we shuffle true. So every time that you start the process of running the batches, the data is going to be shuffled. So a little something different there to give you some insight into loading things. We can print the train DL just to get a feel for it. You can see it's an object in Torch. All right, and that's it. We are now ready to set up the Now we have the neural network architectures. So You know how to build these network architectures. We've done them from Iris for wine for classification. Now we're going to do this again for wine, but for regression. That's the only difference. But as you can see, pretty much 80% of this is the same, and you should understand how it works. So let's go ahead and do that. All right, so create the cell as a markdown. All right. So I'm going to copy this. All right. So now let's analyze this class, right? So the same thing as before. This is going to be, these are regression problems. So you guys took in your statistics class, you know that there's regression. Within regression, there's the more basic thing of linear regression, right? And then you have also non-linear regression. So the non-linear regressions are the things that have the more advanced concepts of neural networks, right? And the linear regression is just a basic, very linear function that you guys looked at in your stats course, or you learn how to calculate manually all the components. All right, so let's take a look at this. I'll do a linear regression and then a nonlinear regression. But you can see I define the class as linregnet, okay? NN.module, okay? So we inherit that. Then it's got the two functions, the init function, which is the constructor, and it's got the second function, which is the forward function, okay? So in the init, the same thing, we're going to pass the x means and x deviation so that we can scale the data. We initialize the inherited class, just like before. We load the x means and x deviations, and then essentially, this is the whole neural network for linear regression. So a linear regression, maybe you took it in your class, nobody said to you that it was a neural network. It's technically not, but it fits within all the machinery that we're doing in its most basic form, as it is a dot product. And that's essentially what everything is a dot product from your perceptron, right? You guys remember that one. So essentially, notice that all I do is I create a linear one. I use this NN linear. Remember the concept? I still need to show you this, but NN linear is just a dot product between the X's and the W's. So essentially here, this network is inputs of 11 and one output of 1 because there's only a regression. You guys see this? That's it. This is the whole neural network, right? And now we can perform the inference. So remember, you give it an X. That X, right, is this one minus all the means divided by the deviations. Now you have the scaled or standardized version of the X data. And then notice X just goes into linear 1, and that's it. Done. Does this make sense, guys? Notice there's nothing else going on. I just, you can ignore this. And you essentially return that Y pred. That's a linear regression. So let's go to the notes, as I may have a graph that resembles this one. So let's go here. Because you guys are reading these notes, I will just point out, we go to topic notes. And it should be one of these. So it's a regression. So we are building, a linear regression. Something like that. That's what the network looks like, except that instead of having only 2 inputs, as this one does, it has how many inputs? How many neurons in this layer for our wine quality data set? 11, very good. And then there's only 1 output. So there's essentially 11 weights, there's 1 bias, and that's it. That's a linear regression. You see, but you can code them in the same framework that we're doing for neural networks. It's not a neural network technically because it doesn't have a hidden layer and because it doesn't have activation functions. That is literally the difference. If you break all these things down, they're just dot products between X's and W's with hidden layers, which means layers in between other layers, and activation functions such as the ReLU, the sigmoid, the tan, the softmax. That's it. That's what neural networks are, right? And so, you know, this is like, if you think about how many neural nets we've done so far, right? Perceptron, Hopfield networks. We did iris, wine, and now regression. This is like at least the fifth that we've done. And it's all the same ideas. All right. So yeah, so we can you guys should read through all this. I'm wondering if there's have a graph here somewhere. Don't remember. Not like that. Yeah, so okay. So this is more classification, but it's more like that graph. Okay, so we can go back now to our code. So we define this function. So I'm going to go ahead and run it. All right, so it's loaded. I've done my linear regression. I'm just going to stick to this one, and then we're going to do some type of a nonlinear regression. So I'm going to keep going here. Now, yeah, I'll skip the multi-layer perceptron for now. I'll come back to that. And we have a deep DLNet. Oh, and I do have this linear plus nonlinear. This is an interesting concept. So we'll take a look at that. But now, let's do the training loop, right? So we are ready to train with a very simple linear regression model. And then we'll just play with other architectures. So notice the training loop function, same concept that we've been playing with, a few modifications maybe. So that's the train loop. I'll come back to it in a second. Let's instantiate the aspects here. All right, so I'm going to use the linregnet first. I'm going to comment out that, and I'm going to enable this one. I give it the X means and the X deviations, right? I create my optimizer, which is the thing that will take the computational graph. You know, every iteration, it'll calculate the gradients, which is doing the calculus part and determining if the weights are going to be added or subtracted given the learning rate, essentially. So you can see torch atom, I tie to this the model parameters because that's the weights and the biases. I give it the learning rate. This is also different. If you notice here, I'm using MSE loss instead of cross entropy. When we're using a regression, we essentially use, you know, mean squared error or a variant of that. And when we do classification, we use cross entropy. So I'll discuss these two concepts in probably on Wednesday. But yeah, that's essentially that. And then we have our training function, train loop, which takes in the number of epochs, the model, the loss FN, and the optimizer. So now let's take a look at the train function, which, as you can see, essentially two for loops, just like before. The first for loop is the number of epochs that we repeat the whole process. I think it's 100 in this case. Then we, from train DL, we are going to grab in batches XB and YB, right? So 16 X's and 16 Y's. So every time I grab an XB from a batch, that's going to be 16 by 11. And when I grab a YB from a batch, it's going to be 16 by Y. $16 by 11 for XB, 16 by 1. Very good, because it's the regression value. You see that? You always want to think in terms of that. Then what do? We give XB to the model. The model predicts Y pred. And what do? We compare Y pred to YB. That's going to be the minimization with MSE, minimizing the error. Okay, the difference. And that loss, remember that so far, all we've done is created this computational graph in memory, right? Data is connected to operations and everything is connected finally to the loss. And then here, every iteration, we perform the calculus part and update the weights. Do you remember? So every iteration we predict, we compare the predicted to the real. Okay. And we need to minimize that error, which means we need to move. Remember that graph that I gave you, right? We need to move down that gradient. And if we visually look at it, we know how to move it, but we need to know how to do that by doing some calculations. So that's where the calculus part happens. So we calculate the gradients here and then update all the way here. These three lines are always there. They do all the heavy lifting in PyTorch. And then, whether you're training a GPT or you're training this, you always use it. Very constant, very consistent. This, as you probably have seen so far, this is for printing the loss values, which our objective is to minimize these loss values. Any questions on this? Same function as before. As I said, so it starts to get repetitive, actually. All right, I hit the star here, and as you can see, the model is now training. There we go. It starts at 23.54. These values are different than the usual 0.0 that we have, because in the 0.0 that we have a predicted label and a real label, which is usually very close to each other. These are regression values, so they can be a little bit higher. All right. So now let's go ahead and take a look. So also you can see it's kind of slower. And I think it's going to do 100 iterations. Maybe the next one is 20. Okay. Oh, it's much slower than before. Yeah, this computer is not kind of plugging in. It slows down. Dell XPS something. Oh, there we go. So it's 20. It's a bit slow. But, all right, so let's leave it there for a second, right? Let's let it train, and then we can continue going through the rest of the code, right? So obviously, once the model is trained, the next part would be to evaluate the performance. And because it's a regression, it requires a different kind of performance metric. So it's not going to be the precision recall F measure. It's going to be a little bit different. So I'm going to go over here and I'm going to use something called the R square. It's going to be the metric. Now, you guys have used this already because you did, we did something in Y. Did you install it first? Uh, when you did the installation, did it complete? Did it say successfully installed? So, yeah. All right, okay. Let's go up here. So, yeah, I did install XGBoost, and then I just did import XGBoost as XG. happens when you do that? Running from the terminal? It's not from the terminal, sorry, from the, yeah. It's exclamation. Yeah, something like this, but sometimes when you do stuff like this, you have to restart the kernel on your kernel. Did you do that? It works for you? Yeah. All right. So we can come back to that. All right. So let's take a look at the model. So it says 60th iteration. All right. So now we're going to figure out how to measure performance for a regression model. So we're going to evaluate obviously on the test set. I'm going to grab this statement. So I'm going to give it X test TR, if you notice, right? So I'm giving it the test data, the X data. I'm going to run it through the model, and it's going to predict regression values, widespread test. I have the corresponding regression values for these inputs. So they should be, and we can take a look at the shape also. We can print the shape. Okay, so there should be about 1,000 samples. Oh, this is going to run once this finishes. All right. So then all we have to do is import a function from scalar. I'll show you how to do that in a sec. But essentially, we're going to use this function called R² score, and we're going to compare the real Y test to the predicted Y test. Okay, and I'll explain to you what this whole NumPy and detached things, what they are. So let's add our R² score. We have to import that from an scalar. So I'm going to go to the top. Okay, so in here it is. So from scalar metrics, so scalar we already installed, so we have it available. We just have to make sure that we've added this entry into our journal. Okay. Over here, save it. And you can see from scalar metrics, import R². So R² is a metric for regression. It's called a coefficient of determination. And essentially, you want that value to be higher. Right? And that tells you when you're comparing two models, you pick the one that's closer to one that has the highest value. You see that? So there's obviously some math and some questions on how that works. But essentially, as far as interpreting what the output means between, so if we're comparing our neural network regression models for XGBoost or something, right, we would pick the one that has the highest cluster. All right, so I believe it finished training. And so they did a 100 iteration. So now let's run this one. So now we predicted the values, and the shape is 90 by 1. Right, that's my Y pad. So now I'm going to compare. I'm using R², this Y pad test to this Y test TR. Notice that this part is very simple. All I'm doing is R squared scores a scalar function, so I'm just converting it to NumPy. So I'm using the torch tensor version of the data. I'm using a NumPy version of it. And I do the same for the predicted data. Notice also that there's this other thing called Ph.D. This might be a very weird thing, but what happens is when I pretest, right, where is it coming from? It's coming from the model. The torch tensor, it's a prediction from the model, but it's still attached to the computational graph. And when you try to modify that with something like this, whenever you cut the tensor, it might affect the whole graph. And so when here we don't need to use the graph anymore. You have a result already. So what you do is, and you'll encounter this a lot, that it's going to give you an error message that says this tensor is still attached to the graph. Please detach it, right? And so that's essentially what we do here. We detach it from the graph, and it's now like it's a separate thing that we can manipulate without affecting the computational graph. So that's what I'm going to do here. I'm going to hit run, and you can see that it gives me an R square of 0.22. That's it. Now I have a metric that I can use to compare between all my other models. So this was the simplest regression model at 0.22. It's not a horrible value, right? But obviously we want it to be higher and closer to 1. So the question is, I don't even know, our neural network's going to give us better results, right? So let's play with that idea. So now all I'm going to do is I'm going to create a new architecture, which is going to be the multilayer conceptual regression. So now this was a linear regression. Now we're going to try out nonlinear regressions. All right, so I'm going to go back to my Jupyter notebook over here. And we're not going to do hold on. We did this, and we've evaluated the model. Sometimes I like to print the results just to look at them. You can see how, I'll show you that in a second. I do that, but this is a very long list. Let's just try the architectures first, okay? So we did linear regression. As you know, all we have to do is really just change one line of code, add the new class, and rerun everything. So I'm going to go, I've done lin regression net. Now I'm going to do multilayer perceptron. Okay, and we'll talk about it. But you guys should understand now how this works. So let's add it here. Okay, or actually, let's add it above. So that way I can just repeat everything. So it would be here, right? So let's add it here. All right, so this is an MLP underscore net. Look at how it's very similar. We inherit an N module. We do the super init to initialize the inherited class. We provide X means and X deviations to standardize. That's straightforward. Now, what changes is here, right? If I start adding more of the machinery of a neural network. So now I have, notice, it's still 11 neurons as an input, right? Just like before, 11. The output is 1. You can see that there, 1. But in between, I'm going to add now a hidden layer with 8 neurons, and it's going to have an activation function called the sigmoid. You guys see that? So every neuron is going to be go through this activation function, which will cut the range to between 0 and 1. So now let's take a look at the inference function. So we give it x. X goes here, minus the means divided by the deviations. Now we have the standardized x. Great. Then we give the x to linear 1. That's the 11 to 8, right? So it does a dot product between the 11 inputs and the weights to produce a layer of 8 neurons. That's here. And then these 8 go into the activation function, which is sigma to produce this X. There's a dropout that I'm adding here. Dropout is something that randomly it's going to drop some connections. So it's like saying there's 11 ways, right? 11 connections, but I'm going to drop a few of them randomly. And every time I'm training, I do that. And essentially, you're forcing the model to kind of be more efficient in its learning. Once I get this X, that X goes into linear 2. So what happens here? Who can tell me what this looks like? X goes into linear 2. What does that mean? What is the shape of X? It's 8, right? And it's multiply times 8 ways to produce how many neurons? 1. This one over here. And notice that that neuron does not have an activation function. That produces widespread, and then widespread is essentially what we return. Does that make sense, guys? And that is the multi-layer perceptron implementation. This is now a nonlinear regression. Okay. So in theory, nonlinear regressions are better in theory. All right, so let's go ahead and load that one in memory. We know it's called MLPNet. So now I'm going to comment this one out and enable this one. I'm just going to call it MLP. MLPNet. So this one, 11, 8. Right, that's the neural network what we're creating right now. All right, so let's go ahead and run it. That's all we have to do. And we start the training. And from there, notice the value is 1.2 now. And that's it. Any questions? We just repeat the exercise. We want to make a note of the previous R square. It was 0.22. So our goal is for this to go up. It also seems that this is faster, right? All right, so there we go. 40 epochs. You have to get to 100 epochs. All right, 60. So remember, your goal is for this loss to go down. If you notice 123, 35, 61, 36. So sometimes it does go up. It's just the nature of how it is. And it's almost done. So what do you guys think? Do you think this will be better? So we need to beat this score, right? 0.22. So first we did entirely a linear regression. Now we're trying a multi-layer perceptron. It's finished training. Hit run. Right, so moment of truth here. 24, a little bit better, right? From 0.22. Not that impressive. You guys see that? So what's the next thing you do? So now deeper, go deeper, right? So add another layer. So I'm going to repeat that now. I'm going to go over here. And I'm going to grab this architecture. Okay. Control copy. All right. So we're going to add DLNet. So deep learning with 2 hidden layers. Yeah. You can see it's pretty easy now. Still 1 output, but now we want 2 hidden layers in between, essentially. So let's take a look at it. DLNet, inherit the class, super, X means deviations. Here's the architecture, if you notice. So we've got 11 to 10. So that means this one is 10. Then we have 10 to 6. So that means this one is 6. And then we have 6 to 1. So the 11 inputs are the same, the 1 output is the same, and the activation functions are this thing called ReLU. So ReLU is an activation function that if you have negative values, it makes them 0. If you have positive values, it just lets them through, okay, whatever they are. All right. So it's a very popular activation function. And so you can see that here we have essentially now we build the inference function. So we take x's input, x minus the means divided by the deviations. This is our x. And this x goes into the first linear. That's going to be the vector of 11 times the 11 weights, and it produces a new layer of 10 neurons. Then those 10 neurons are here, are going to go through the activation function, activation of 1, which just maps those values using rel to produce this x. Then this x goes into linear 2. Linear 2 is the layer from 10 to 6. So it's the dot product of these 10 inputs and the 10 ways to produce a layer of 6. Okay? Right? So that's linear 2, 10 to 6. You can see that there. And this x now, this x here, goes into activation 2. That's another value function, right? And that produces this x. I didn't use dropout here, if you notice. And then this x goes into linear 3, and linear 3 is from 6 to 1. 6. So these 6 neurons times 6 ways to produce 1 neuron in the next layer. That's essentially. And then we just return what we get. So this class is called DLNet, so we want to see what happens. All right, so I just ran it, run the training loop. This is going to be DLNet now. Whoops. DLNet. So we use another class, right, and let it train. What do you think? You think it'll do better this time? You don't know, right? But this is the whole process of machine learning and deep learning. Right? So this is how computations work. You get the data, you try architectures, and you hit a limit, something new with DL, and then you have to try new algorithms. So there's the loss of 0.65. So here I tried this one. It gave me a 0.40 previously, but if the data is random, that's not a guarantee. I could have been on high side for that particular. But we'll see what happens. Still training. Oh, it's much slower. I know my computer is very slow, but it is slower because this is a deep neural network, right? So obviously, it starts to make you want to have a GPU and everything. Right, there's a sec, so we're at 20 now. All right, well, it's doing this. There's one more technique that I'm going to cover, which is a very interesting one. It's called the linear plus nonlinear. And what that does is it's kind of very clever idea. It's essentially a multi-layer perceptron and a linear regression model all in one. So that's all in the same class. And what you're kind of doing is you're training two models, right? And then you're kind of using them together. So the intuition kind of here is that some problems can be, the majority of the problem can be linearly separable, and then there's like one little piece that isn't. And so you kind of create, you want it to mostly be linear, except for that additional part. And so this is kind of a clever way of creating two neural networks within the same class. If you notice, all that you do is you create one network here, one network here, and then before you get the predicted value, you add them together. And because they're learning the weights, this training, right? It's going to learn the weights that allow it to, that work best for this. So this is going to be the linear part, and this is going to be the non-linear. So we'll try that one out as well. But as you can see, it's essentially just two separate networks that are then at the end linked together by just adding them together. This is pretty slow. So I guess it's gonna take a while. So I'm just gonna start coding this part here. This is the linear plus nonlinear model. I'm gonna copy this one. All right, so we're gonna go to where the neural nets are defined. All right, so while the DL net is training two layers, let's talk about this linear plus nonlinear. So linear plus nonlinear is essentially F1 plus F2, two neural networks. And before you take a final prediction, you just add them together. So here, the same thing, we have our init function and our forward function. We inherit the init module to instantiate our class. We pass F means and F deviations, just like before. Now notice here that we're going to have F1 linear 1 and then F2, so F1 and F2. For F1, because it's just the linear regression, essentially, we just have this layer of 11 by 1. Here we have and that's one neural network called F1. And then we're going to have F2, which if you notice is going to be this one, and this MLP essentially. Notice from 11 to 1, but in between there's a hidden layer of 14. That means there. That's the 2. You guys see that? And there's an activation function called a sigma in there. So when we put the whole thing together, X comes in, we scale the data, then this X goes directly into F1 to produce F1. So that's this. Call it F1, this just one to run. And then over here, we have another function F2, which takes the same X. You see that it takes like this X, or actually this X. So it goes into both networks kind of at the same time, parallel. And this one, F2 goes through that whole F2, 1, 14, 0. And then what you do after it, you just take F1 and F2 to predict the final value. Because the model is learning the weights, it will eventually just, still need to learn, like, it almost says, like, which is more important, the linear or the nonlinear, right? And so, add all of these together to produce the red regression. And so it's another approach. It's very interesting. I've used this a couple of times, and I think it's good. I think it works well. We'll see right now. It's definitely a clever thing to try. All right, it's almost done with the training. Right? So while that's going on, I'm going to grab this. In the campus here. I'm going to copy these. Here. So, and we'll just see how well it does. Any questions? Yes. Okay, great. Yeah, so there's nothing else I can do until I finish this. The last part of today will be, I'll show you how to print out the result and also how to do the XGBoost. It's still training. All right. So the next thing we're going to do is, once it finishes training the neural network, we're going to instantiate an XGBoost regressor. Remember, this is like a tree type of data structure. We're going to use the full parameters here. And notice that all we do is we take X train and Y train before we convert them to torch tensors. We're going to fit the model, and then we're just going to predict. And then once we've done prediction, we can measure the performance of the R square and go from there. So this is a very easy, actually, algorithm to use. XGBoost is written in a very simplistic way. So they look at that. All right, almost there. I'm going to write down here XGBoost. Okay. So you're gonna, like I said, we import XGBoost. Then we're going to say XGB dot XGB regressor. We use these as the full parameters. And then we're going to just train. It has a similar approach to sklearn. So we trained an X train and Y train. All right, but it seems that I finished. Okay, finished right. All right, so that's using the DLNet, you remember. So let's go ahead and run and shapes 31. So the R square has gone up, right, to 0.31. I think we went from 0.22 to 0.24. Now 0.31 seems more significant. Does it make sense? So deep neural network, two hidden layers gave us slightly better results. So what else can you try before you go to XGBoost? Well, we could try that linear plus nonlinear. If it's too slow, I'll kind of just skip it, okay, because it might be very slow. But let's try. Let's see if it runs fast. Oops. Oh, yeah. You should define it. All right, let's run this class. So let's load it in memory now. Uh, yes. And then linear plus nonlinear. Okay. There was no attribute F1 linear. There might be a little here. You try to say, yeah, there's an error in here. So let's see. What's that? Yeah, I'm looking. So yes. Yeah. So there's F1 linear one, F2 linear one, F2 exclamation one, F2 linear two. So self F1 linear one. Oh, linear one. See here. Listen. You guys see that? So you just have one in there, self F1 linear, and then here, these are correct. Yeah. Got it? Everyone got it? Just added that one. All right, so let's load it. Hopefully that will work now. Let's see how, and this is linear plus nonlinear. All right, so there it goes. Training. Okay, that's the first one. Let's see how fast it is. But yeah, this is essentially how you would tackle a problem like this. Every day I create several neural networks, run them, train them. And then for this type of data, I would definitely always recommend XGBoost. And may turn out like XGBoost the best. It's a tree-based neural network. So these networks are essentially like you look at a feature, like feature F3, and the model needs to learn, okay, if the feature is less than 5, then I go in this direction. If it's more than 5, I go into this direction. And then when it gets to the next point, you look at another feature, maybe feature 1, and the same thing. Oh, if it's less than 7 this way, if it's more than 7 now. But it keeps doing that. There's an algorithm, obviously, that creates that tree. And it is a tree. Yeah. And then XGBoost can just be one of the very advanced implementation of training algorithms. All right, so we're writing the last one. Seems that it's going to be slow too. Did you write all right there for your linear plus nonlinear? What's the R square? So it's higher. Is that higher? Okay. You guys also okay. So yeah, good. So 0.37 with linear plus nonlinear. So you're winning. The competition essentially you win. So yeah, so 31 Let's see what I get. The problem with this is you can't just trust that one result. You should run it like 10 times. And that's why we use that C. And you randomize, you run it 10 times and you randomize it, then you take the average of that result. And that's the more trusted. That's what I recommend because maybe let's say that I got 56 here in this run. I'm very excited, but when I go to the competition, I may never be able to. But instead, if I get iterations where I'm randomizing the data every time, then it creates an average that's more like something you can expect. We're going to have to wait. But yeah, we're almost done with regression, as you can see. And then on Wednesday, I will definitely do cross entropy. We'll start with entropy and then cross entropy and explain what that loss function is all about. And then I also need to put the linear and that linear. That's just that same dot product from the pre-product. But yeah, you're pretty much graduating from this at this point. We've done all the basic things. If you read chapter 4, you know what I'm talking about. I just have a few additional things to cover. And then after spring break, we'll start probably with more advanced things like image CNNs and things like that, ResNet, and of course you'll have the homework. Yes, still going. I think XGBoost does run fast, so let me finish adding the code for XGBoost. I guess while it's still training. So I'm going to need to predict, obviously. And that's going to be the values. And then we just need to measure performance. And this is just, you can also deploy an XGBoost model on the web. But I need to do a lecture for that. It'll probably be after the break. Yeah, so we're almost done. All right, 80. If you guys have, ever a problem with regression now, these are all the tools that you should definitely use. I mean, this can, the only thing I guess I haven't shown you is what if you had two regressions that you're trying to predict? So, for instance, what is this example about? It's wine quality, right? So, and we're measuring like the rating, right? But it could be that you're also, what's another thing that we would want to predict? Maybe the price, right? So you say, okay, I have this data, I'm going to predict the rating, but also how much I'm going to charge. So let's say, $47 or $49. So you could actually have two outputs, two regression outputs. That's called multi-output. What I have found, honestly, it's that it's better just to create individual models. You see what I'm saying? So you would create one model for this one and then another model for that one. Because what ends up happening when you do something like this, which is convenient, but it's going to be a balance between the two because it's the weights, right? So the weights are going to be a balance to get, the best performance possible for both. So it may be better just to have one model each. One for rating and one for price. Do you guys see what I'm saying? That's what I have seen in my experience, but you could also have one single one. All right, it looks like it finished. So that was the linear plus nonlinear. I believe my highest was 31. So let's go ahead and hit run 30 actually. So it went down. So, but you got a 37, right? I don't know if you've tried running it again or something to see if, but obviously, as I said, it's not just about the highest that you get. Instead, it's out of 10, what was the average? And that's really what you want to go with because you want to be able to replicate those results. All right, so we've done this. So with neural networks, I was only able to get to as far as 31. Now let's go ahead and try XGBoost, okay? And see what happens. So XGBoost, as I said, not a neural network. For this data is called tabular data. So tabular data is essentially regression data, where you have like this pandas data frame, like this one here. So this is called tabular data. And it has been found in many Kaggle competitions that whenever you have small like this, small tabular data, XGBoost models actually do really well. And so that's why I'm showing this to you guys here in the context of neural networks. Let's go ahead and see what happens. I'm going to instantiate the regressor. Done. I'm going to fit with my X train, Y train. All right, so it's training. This algorithm, as you can see, it finished already. It's designed very efficient in the background. So let's predict on the X test. Okay, that's done. I actually want to print out the shape just in case. So Y print should be about 1,000 by 1, if I remember correctly. So Y print that shape. There's 980. All right, and now I'm going to calculate the ER square, 0.40. You guys see that? Better. So if you're in a competition, doesn't matter if somebody's bringing all the fancy neural networks. I love PyTorch and neural networks, but I want to win, right? And this will get you to win. Do you guys see that? Yeah, there you go. Super efficient. This implementation of it, I read a bit about it, and I know it's very efficiently implemented to be really fast. There you go. XGBoost, we covered it. I don't know that I'll have time to cover the actual algorithms underlying of trees, but you definitely have this as a tool to use. And if time permits at the end of the semester, I might come back to XGBoost. But today's lecture was really about regression models. Do you guys understand regression models now? Should, right? Really, everything was the same except for the last layer. No softmax, which we had in classification, and so on. All right, so we're almost at the end for today. Go through this notebook. I'll load it in a second on the 2025 repo. Please, again, you should be reading these materials here. Topic notes, as we have covered a lot of it already. On Wednesday, my plan is to cover this is probably the hardest topic of the whole semester, which is not that hard, but it's a little bit harder, which is going to be this is MSE, but binary cross entropy. Okay, so we'll cover this entropy, cross entropy, and all that. And so I'll go over these. This once again goes back to the idea of the bowl. You remember the MSC bowl and gradient descent? So you can see this is kind of the same idea. If the weights are here, what do you want to do? This is the cost, so you want to minimize it. So you want to go in that direction. Similar idea, it's just that it's a different function for classification. And I will discuss that on Wednesday. Got it? All right. I'll stay for a few minutes if you guys have any questions. Otherwise, we can stop here. And I will, like I said, I'm still working on preparing that new homework assignment for you. All right. Stop the video.